All right, number one, we have a piecewise function f, and we're going to consider this graph. I'm going to just graphing, it's not part of the problem, but it may help us to understand it. At which x values are there discontinuities, and then classify them as removable or non-removable. So I'm just going to do a quick sketch of this piecewise function. And where the x values are negative, we have the equation x minus 1. So it has a y-intercept of -1. And it has a slope of +1. So we have a line, and if it were to go into the area where the x values are positive, then it would continue with a slope of 1, but we just have this where x is less than 0. And this particular one here, this particular piece is not defined when x is exactly equal to 0. So for the moment, I'll put a hole there. And then for the next piece, and this the second piece is defined where the x values are positive but less than or equal to 2. And it's negative x minus 1. So again, it is going to have a y-intercept of -1, and then its slope is going to be the -1. And it goes up to 2. But not actually include, or actually, no, it is defined there where x is exactly equal to 2, and it has a slope of -1. It's going to go in the downward direction from 0 to 2, and it is defined where x is exactly equal to 2. So I'll make that in filled in hole, and then x plus 5 for our x value is greater than 2. So that y-intercept is going to be up at 5. But what I'm going to do is, let's see if I can. If I were just graphing that, not taking into account that it's a piecewise function, but if I were just to graph x plus 5, I've got my y-intercept. Actually, there's not going to be a lot of room here to do this, but and it's not defined for x exactly equal to 2. So I'll put an open hole, but it has a slope of 1. So it'll go up like that. All right. Answering this question. So at which x values are there discontinuities? So there's a discontinuity there because there's a hole. So at x equals 0, there is a discontinuity. And if we wanted, is there any way that we could, if we wanted to, I mean, we can't just change a function, but if we wanted to, could we add in just what would define that point there where x is exactly equal to 0? Because this function is not defined where x is exactly equal to 0. But if it were, could we fill in something there? -1 at x equals 0. Not 10. And if we'd had that, then we would be able to fill that hole in, and then we would have a continuous function through that area there. So if we could do something like that, then it's called removable. We could just kind of do something simple if we wanted to and remove that discontinuity. But the second one, it's discontinuous because there's a jump. So it's discontinuous at x equals 2, and there's nothing that we can do to bring the two pieces together, that piece and that piece. There's nothing we could do to bring them together. So this is non-removable. Compute the limit. And just to write the answer, because we're just going to take a look at this graph. So the limit as x approaches 5 of f. So 5 is way out here. And we're on the green part, So let me extend the green part a little bit more. So this just keeps going up and up, that green part. At 5, it will be defined with no problem. So we, f of 5 is just, or f of 5 is just some number. And so for x equal 5, we're talking about this third piece. This is the part of the function that we're on. So this is going to be the limit as x approaches 5 of x plus 5. And there's no problems there. So we can just plug in the value of 5 for x. And then compute the left-hand limit as x approaches 0 from the left. So where are we as x approaches 0 from the left? We're in the negative area there for our x value. So we are on that first piece there. And we are approaching 0 from the left, which means we are traveling along that first piece there and moving toward that place where there was a hole. And that's the answer. And we just need to write that down. So basically, we're going to use, even though this first piece is not defined at 0, that's the point that is approaching. So we'll just plug in 0 into that first piece, and that will be our answer, -1. Okay, number 2, using rules for derivatives. Differentiate these. So f prime, and also I like to see that you use the right notations. So I'll say f prime, and this is just the derivative of 2x, the derivative of 2x plus 1. And this is going to be equal to the derivative of 2x plus the derivative of 1 using our rules of derivatives. The derivative of 2x is just 2, and the derivative of 1 is 0. So that's it. For part B, we have an x squared there in the denominator. And so to make this a little bit easier, I'm going to rewrite this as minus 3x to the minus 2 power, and then minus 2. So using the right notation, either y prime or dy dx in this case, the derivative of minus 3x to the minus 2, well, I take this minus 2, multiply it by the coefficient that's there in front of the variable. So it's going to be positive 6, and then subtract 1 from the exponent. So that would be minus 3. And then the derivative of minus 2 there is just as a constant. So the derivative is 0. All right, for part C, very similar to B in that I'm going to rewrite the square root of x in the denominator as x to the minus 1/2 power, which is equivalent. Now I'm going to take the derivative of this. I'll mix up this notation. So we'll say d dx of f. The derivative of that first term there. So we have minus 1/2 times minus 5. That's positive 5/2 x. And then we have minus 1/2 minus 1. That's going to be minus 3/2. And here we don't have a constant now for our second term. So we do need to write something down for that second term. And that's going to be 4x. All right. For D, technique I'm going to use here, you could, if you wanted to, use the quotient rule, but there is no need to in this case, because I can rewrite this. You wouldn't have to put this many steps, of course, but I'm going to rewrite. I'm going to just basically undo this fraction, make it sum of 3 fractions, and then simplify. So 3x squared over x is just 3x. x over x then is 1. And then we have 1 over x, which is x to the minus 1 power. So the derivative of y then is going to be the derivative of 3x is 3. The derivative of minus 1 is 0. And the derivative of x to the minus 1 is going to be minus x to the minus 2 power. And for part E, f prime. So I have the derivative of, this is basically 1/2 sine of x. So we have a coefficient of 1/2, and then the derivative of sine is cosine. Derivative of cosine is minus sine, so I'll put minus sine x. And then we have a derivative of a constant, which is just 0. So that's the answer. And number 3, this problem, by the way, is similar to the problem that you may have seen before about the silver dollar being dropped. So a phone is accidentally dropped, in this case, not thrown. So that means that the initial velocity is 0. It's dropped from an apartment window that is 400 feet above ground level. The position function, just in general, for a free falling object, and this is on Earth, this minus 16 right there, that is what it would be on Earth. But there is just the general position function where v naught is the initial velocity and s naught is the initial position in feet. T is in seconds. So what is the position function for the falling phone, which means what is it with the numbers filled in? So we have s of t minus 16t squared. Our initial velocity was 0, so I'll leave out that middle term. And then our initial position is 400 feet. Derive the velocity function for this position function, and the velocity v of t is going to be the derivative of s of t, and this is going to be minus 32t. That's the derivative of minus 16t squared, and then the derivative of that constant is 0. So we're done with part B. How long does it take for the phone to hit the ground? Another way to ask this question is, how long does it take for s of t to reach 0? Because it's 0 at ground level. So we're going to take our position function, and I'll just write it like this. It's minus 16t squared plus 400, and set it equal to 0, and solve for t. Okay, there's a couple ways you could do this, but divide both sides by 16. We get t squared is equal to 25. T is plus or minus square root of 25, which is plus or minus 5. But negative 5 seconds doesn't make sense for us, so the answer is 5 seconds. And then part D, how fast is the phone moving when it hits the ground? And so, and this really, I mean, it would be better if it had said, what is the velocity? But if we, because here, how fast are we asking for the velocity, or are we asking for the speed? So I'll just say my intention here is to ask you for the velocity. And since it's moving downward, we know it's falling. So we should expect a negative answer here. But all this is really asking is, what is V evaluated at the point in time where it hit the ground, which we just found out was at 5 seconds. So we just simply plug this in. So this should be minus 160 feet per second. All right, number 4, differentiate all these functions. So, there's a couple ways you could, spend a few minutes and multiply all that out and just take the derivative of each term. But we're going to use the product rule and using the right notation. So f prime. This is going to be, and when you have a product of functions, basically, then well, let's suppose that we have f here, but let's suppose it were something else like h. We have some function h, and if you can split it up as a product of f times g, then the product rule for h prime, the way that I usually like to do it is I say f prime times g plus f times g prime. And the book had that in the reverse order, but whichever way you prefer to remember it. So we're going to take the derivative of this first factor. And I'm just going to do it without rewriting it. So you can see here that that first term is the same as minus 8x to the minus fourth. And this one is minus 3x to the minus 2 power. So we have minus 8 times minus 4, which is positive 32x. Now we have to the minus 5. And then minus 3 times minus 2 is plus 6 times x to the minus 3. That's the derivative of that first factor times the second factor left as it is. So we've done this first part of that product rule. Now we need to do the second part. So we're going to add on. Now we take that first factor, leaving it as it is. And then multiplying it by the derivative of that second factor, minus 15x squared plus 2. And just to make it easier for me to grade, because from this point, if you wanted to simplify it, if it wasn't designed to quickly simplify, then it might take you quite some time to do it. So just leave it. Don't do any simplification to it to make it easier for me to grade. For part B, we have the derivative of this exponential. And if this was just e to the x, then the derivative would be e to the x. But we have e to, you can think of it as a function. Let's say, call it function u. So if we have e, the derivative then of e to the u of x, we'll say, this is going to be equal to e to u of x, and then multiply by u prime. That's the application of the power of the chain rule. So this is just e to the 2x squared, and then multiply it by the derivative of 2x squared, which is 4x. All right. C, there's two ways you could do this. You could do it the hard way, or you could do it the really, really, really easy way. You should know, if you don't even know any other trig identities other than the real basic ones, but if you don't know any other, memorize this one: sine squared plus cosine squared, which is always equal to 1. So f prime is just 0. So you could, I suppose, you could say f prime is equal to the derivative of sine squared, which is going to be 2 times sine of x, and then times the derivative of sine, just cosine of x. And then minus or plus 2. Well, it'll end up being minus, but then the derivative of that second term, we get 2 times the cosine of x, and then times the derivative of cosine, which is minus sine of x. So we have 2 sine x times cosine of x. And it's going to end up being minus 2 times sine of x cosine of x, which is still 0. So for D, I'll say dy dx this time. The derivative of sine, and just like earlier when I was saying that u is a function, here we have, we'll say it's a sine of some function of x. What is that then? It's going to be the cosine of that function and then times the derivative of that u function. So this is going to be cosine of 3x squared and then multiplied by the derivative of 3x squared. All right, for E, the derivative of a log. So if it was just log of x, natural log of x, then our answer would be 1 over x. But because we have our log of this function, 3x squared, then we are going to apply the chain rule. So f prime 1 over 3x squared, and then multiply this by derivative of 3x squared, which is 6x. So it's 6x over 3x squared. This one you should, if it's something this simple, you should simplify it. So this is 2 over x. And so by the way, just, what we did over here, if you have natural log of something other than just x, then you can think of it as a function of x, u of x. And that derivative is going to be u prime over u. And f, for this one, I'm going to use the quotient rule. So g prime is going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. This is all divided by the denominator squared. So sine squared of x. Right, number 5, find the third derivative. So first derivative, we have the derivative of x to the fourth, so that's 4x cubed. And then the derivative of e to the x, which is just e to the x. Then we have the second derivative, which is going to be the derivative of f prime. So we have 12x squared. The derivative of e to the x is still e to the x. And then the third derivative, f triple prime, 24x plus e to the x. Right, number 6, implicitly differentiate this implicitly defined function to find dy dx. So what this is telling us is that we are looking for y, a derivative of y with respect to x. So this tells us that y is a function of x. So we're going to take the derivative of both sides. And I'll go ahead and compute the derivative of the right side. The derivative of a constant is just 0. And let me go through this derivative on the left side. So we have the derivative of y, and y is our function of x. So we'll start out with the, sort of starts out looking like the power rule, but then we have to apply the chain rule, which means we tack on the dy dx. The second term, x squared, this doesn't have y in it. And we just treat that just like the regular power rule. So the derivative of that is 2x. Next, we have minus 2y. So we start out with the derivative as if it weren't a function. So the derivative of 2y would normally be just 2, but y is a function. So we of x, so we put on the dy dx. Same idea for this last term. And then this is equal to 0. So now we have a term here with dy dx in it, and another, but not this one. So what we want to do is the ones with the dy dx. Basically, we're just solving for dy dx. So we're going to keep the ones with dy dx in it on one side and put this plus 2x, we'll move this to the other side and then factor out dy dx. And finally, we solve for dy dx. And in this particular one, we can just simplify this just a little bit. We might as well. And that is dy dx. 7, a sphere is growing at a rate of 2,048 cubic centimeters per minute. The volume of a sphere is given by that formula shown there. And by the way, this is going to be V of R. V is a function of R. Implicitly differentiate the volume equation with respect to T. So we are looking for d dt of this function V, a function of R. So d dt of the left side, this is equal to d dt of the right. And we have 4/3 and pi are constants, but R is a variable. So we just have the d dt of V, I'll write that as dv dt. And then we have the derivative. So R is a variable. We're going to start out by treating this like our usual power rule. We have 4/3 pi, and then multiply this by 3r squared. But because we're taking the derivative of this variable R with respect to t, we need to, if this had been ddr, then we would stop with the 4/3 pi times 3r squared and simplify that. But because this is with respect to t, we're going to tack on dr dt. All right, and then we'll simplify that. So dv dt, these 3's will cancel, and we just get 4 pi r squared dr dt. So for part B, given that the value of dv dt is a constant, so this is, it says that the sphere is growing at a rate of 2,048 cubic centimeters per minute. And that's just a constant, no matter which minute we're in. This is telling us that the sphere is growing at that same constant rate. So, so the value of d, and that's dv dt, the rate at which the volume is growing with respect to time. So that's the 2048, and that is a constant. So given that we know that, find the rate at which the radius of the sphere is growing. The rate at which the radius of the sphere is growing when the radius is 4 centimeters. And this probably could be just this explained just a little bit better if it said, find the rate at which the radius of the sphere is growing with respect to time, but we can safely assume that. So as we said, dv dt, so we have this this formula now, and dv dt is a constant. And we have our 4 pi r squared, and the rate, actually, let me go ahead and fill in. So we're looking for drdt when the radius is 4. So that's our value for r. So it's 4 squared. And then drdt is the variable here, so to speak. It's what we're solving for anyway. So we just do that simple. I'll make this, so we have a 4 times a 4 squared. So this is 4 cubed pi. And let's see, so that is so this is going to be 32 over pi, or approximately 10.186. And so what are the units of the radius? That is centimeters. And the units of time per second. Per second. Okay, so for number 8, find the extrema of the function given there on that closed interval. So this will kind of give us a hint that a good way to do this might just simply be to find our critical numbers and then evaluate our function at them and our endpoints, and just find the extrema that way. And you might want to start by noting that this is a continuous function. To find the extrema, we'll start by finding the critical numbers, which we do by taking our derivative and setting it to 0 and solving. So we have 12x cubed plus 12x squared is f prime. So we'll set that to 0 and solve. So I'm factoring that. And you can see that if you set that first factor to 0, then x would be 0. And if you set the second one to 0, then x is -1. All right, so we have 2 critical numbers, and we also have 2 endpoints. And in the past, we when you were doing this on an exam, there was a chart for you to fill in, so we don't have that. But we're gonna just evaluate our x at 0, -1, -2, and 1. F of x for all those. If you put in 0, you get a 0. If you put in -1, we'll get, this will be a 3, and this will be -4. So that will be -1. If we put in a -2, it's going to be 3 times 16, which is 48. And plus 4 times -2 cubed. So altogether we have 16. That is for the -2. We have 16, positive 16. And then if we put in 1, we just get 4 plus 3, which is 7. So we have a min there. And this is an absolute min on the interval from -2 to 1. And we have a max there. This is our absolute max on that interval. So those are our extrema. All right, so number 9, using the second derivative, find the point of inflection of the function that is given there. So we'll need our second derivative. So our first derivative is going to be 3x squared minus 8x. Our second derivative is 6x minus 8. I'm going to set that equal to 0. So we get x is 8/6 or 4/3. And so this says use the second derivative. And what we're going to do now that we have this point, we're going to check to see the concavity. We're going to just look at the concavity on either side of it, and the concavity we can get that from f double primes. So I'm going to pick a test point. I'm going to pick a test point to the left and to the right. So I will use about 0. We'll use f double prime of 0, and this gives us 0 minus 8, which is negative. So to the left of 4/3, it is concave down. And then 4/3 is 1 1/3. So I guess I'll pick 2 as a test point. So we have 6 f double prime 2. This is going to be 6 times 2 minus 8. This is 12 minus 8, which is 4. So it is concave up to the right of 4/3. And so that is the reason. So there is an inflection point, whether you put where it is in terms of the x value, or you put what it is in terms of an xy coordinates. But our inflection point is at x equals 4/3. And if you need to justify that, you can say, since that is where the concavity changes. Okay, number 10, find the relative extrema of the function given there using the second derivative test. So to do this, and by the way, I recommend that you put this into a graphing calculator just to get at least a little bit of an idea of what to expect. And hopefully your calculator can show you with enough detail, and hopefully you can figure out how to zoom in or out in order to see enough detail to get a good idea of what to expect. But to do this, and in the past, we had a table given to fill out. But to do this, we're going to need first, we need to find the critical numbers. And also there could be some other like areas of discontinuity, might be some places that we want to look at. But so we can first notice that our function is continuous. So we're just going to get our critical numbers by setting the first derivative to 0. So our first derivative then is minus 15x to the 4th plus 15x squared. So set that to 0. And I'm going to factor out a negative 15x squared. And that will leave us with a positive x squared minus 1. And we could divide both sides by negative 15. And then we just have the x squared. And we can further factor. Okay. So from this, we can say that x can be 0, or the x plus 1 set to 0. X is negative 1. x minus 1 set to 0, x is 1. So our critical numbers are -1, 0, and 1. So the directions here say use the second derivative test. And we're going to use that on those numbers we just found. So we'll need the second derivative. Here's our first derivative. So the derivative of that is minus 60x cubed plus 30x. And we want to plug in our critical numbers. And this is the second derivative test is a theorem, and it will tell us what to conclude based on whether we get a positive, negative, or 0 out of this. So let's do -1. Put -1 in there. And we can get the actual number for that. Or you can, well, let's go ahead and let me just do that. So we have, this is going to be positive 60, and this could be negative 30. So the positive wins out. This is going to be greater than. And so from our theorem, this means we will have a relative min. Because f double prime is positive, that means that our function should be, it should be concave opening upward, concave up, and that means that there would be a relative min just in that area around -1. We'll confirm that just in a second with our graph. So let's do f of 1. All right, so here we have -60 and then plus 30. So now the negative wins out. This is less than 0. So it's just around that area where x is 1, then this function kind of tops out. So that means this is a relative max. And then f double prime of 0. If you put 0 in there, you get 0. And this means the second derivative test fails. So what to do? So use our first derivative test then. It says use a different method if the second derivative test fails. So we'll need a test point on either side of 0. So let's say -0.5. And this is in our first derivative. So this is going to be all right. You can either calculate this or you can just kind of look at it and hopefully make a correct judgment that this is positive. Now let's try a test point on the other side of 0. And this is also going to be positive. So since our first derivative is positive to the left of 0, that means our function is increasing. And our first derivative is also positive to the right of 0, which means our function is still increasing. And so we can't have a relative extremum at that point. So since f is increasing on both sides of 0, there is no relative extremum at x equals 0. So we just have a relative min at x equals -1 and a relative max at x equals 1. But this doesn't really answer the question. The question doesn't say find where there's extrema. It says find the extrema. So we need to go ahead and answer that question. And it's real easy to make a mistake here. Which function now do you plug these numbers into? You need to go back to your original. So the extrema itself is a value of the function. So we need to go back to our original function. And f of -1, which we know is going to be our min. And the min itself is so -1 to the 5th is -1. So here we have a +3, and then -5 is going to be -2. So that's our actual relative min. And these things, because they're relative, so our relative min, it's important to say, the point. So the relative min is at -1, -2, and f of 1 then, let's see, so we'll have a -3. So this is going to be a +2. This is our relative max. Technically, that's what answers the question. That is the max, the relative max. And it is at the point 1, 2. So let me figure out where to paste. There's not much room. Give me just a second. I need to copy the picture from another program. All right, there's a picture of the graph. So you can see here, so at 0, this is not a relative min or a max. And so at -1, we had a value of -2, and this is a relative min. It's a min in that area around -1. And then we had a relative max over at 1, and its value was 2. All right, number 11, find the horizontal asymptote of the function given there. And we can just do a quick sketch. We don't even need a calculator for this one. And 1 over x without the +2 would just kind of be like that. So if we have +2, then the whole thing just shifts up by 2. And this says show work. So I don't want to just, use that intuition that I just showed you to answer the question. I actually want to show the work. And this basically amounts to finding the limit. I'll put plus or minus infinity here of f of x, which is 1 over x plus 2. So this is the limit. X approaches plus or minus infinity of 1 over x plus the limit of 2. And so the limit of 1 over x, just, what we learned was that as x approaches infinity or negative infinity, that's going to be 0. And then the limit of a constant is just going to be the constant. So this value here, this y value of 2, that is where the horizontal asymptote is. And you can write, x equals 2 if you want to write the actual equation, or not x equals 2, but y equals 2 is the equation of the line that is the horizontal asymptote. Okay, 12, a rancher has 160 feet of fencing with which to enclose two adjacent rectangular corrals, what dimensions should be used so that the enclosed area will be a maximum? So this is an optimization problem. And I'm going to redraw the picture since the negative image there didn't come out very clear, but we have a rectangle that's split evenly in half. If you couldn't see this picture very well, you would have had to ask about that, but you can see that they've picked variables for us, the X and the Y, but they have X for the width of both sides. So that's how I know they're the same. So it actually doesn't much matter for this, but, and then our depth is Y, and we're maximizing area here, the dimensions, so that the enclosed area will be a maximum. So that's going to be our primary equation. We have an area, which is just going to be the base of this rectangle times the height. And now looking at what else is given, so we have 150 feet of fencing to work with. So if we add up all this fencing, we can set it equal to 160. And so we need to come up with an equation. We have 2x, and then the top part is going to be another 2x. So we have a 2x plus a 2x. And then each of these three pieces here is y. So I'm going to add on to that 3y. And this needs to be equal to 160. So now I want to solve this for one of the variables in terms of the other, and then substitute into our primary equation. So I'm going to solve this for y. And then plug that into our primary equation. And then we'll just have a function of x. And just to emphasize that, I'll say this is a of x. So 2x, I'm going to plug in what we just found for y, 160 minus 4x over 3. And this is what we want to maximize. So let's see, this is going to be 300. This is 320. 320 x over 3 minus 8x squared over 3. All right. Okay, so we will need the derivative, a prime. And by the way, so, what technique will we use? We have a restricted domain. So we're getting ready to maximize the area based on x. What can x be? Well, you can think about, even though it might not make a whole lot of sense for y to be 0, but if it were, that would mean that you would have just a really long and skinny corral. And technically you have two sides though, on the front and the back. So the sides on the left and right would be 0 in that case. And you would have to split up your 160 feet among the two sides, front and back. But x is, split like that. So that means that x can be up to 40. So this gives us a domain to work with from 0 to 40. And, and if x were 0, that would mean that y is going to be 80. But we decided to set up a in terms of X. So the domain for X, a reasonable domain, is going to be 0 to 40. But in any case, and that kind of leads to, what strategy will we have? Well, we'll find our critical numbers and then we'll evaluate our area function at what we find and also these endpoints. We probably won't need to evaluate the area at the endpoints because we know it's going to be 0 at those places. But it will help us if we ever came up with some critical numbers that were outside of that domain, we can exclude them. But in any case, so we're going to take the derivative of A and we get 320 over 3 minus 16x over 3. So set this equal to 0. So 3's will cancel and our x is going to be 20. Okay, so we can go through the motions then of this is our critical number. We can evaluate our area at that in, our endpoints. But we already, just if we found our reasonable domain in such a way that we know the area is going to be 0, but we can go ahead and do this anyway. So A of the endpoint at 0 is, if you plug in 0 there, you're going to get a 0. A of 40, if you plug this in, you should get a 0. And you do. You get a 0. And then our A of 20. So this is going to be 320 times 20 over 3 minus 8 times 20 squared, also over 3. So it's approximately 1,067 feet squared. Now, actually, I don't really, that's actually not even asked for. And let's just read the question again. What dimensions should be used so that the enclosed area will be a maximum? So we found what the actual maximum is going to be, and the dimensions for that are going to be, let's see, the dimensions, we'll say that X is 20. And then we can put, we could put that in here and get our Y. So our Y should be approximately 26 2/3. I'll go ahead and say exactly 26 2/3 feet. So that's our actual answer there. Okay, number 13. Use the properties of summation and theorem 5.2, which you see at the top of the screen, to find the following sum. And the instructions in this case say simplify. If this were on the exam and it does not say to simplify, then save yourself quite a few minutes of extra work, and don't simplify if it does not include that. But here, the instructions say to simplify, so we're going to do all that work. So we have a sum of this, a summation of 3 terms. So one of our properties of summation is that we can split this up into 3 summations. And the first one, we have the summation, our index m goes from 1 to n of the minus m squared. But another property of summation, I'll write this down and then I'll just change it a little bit. But another property is that if we have a coefficient inside the summation, we can take it outside the summation. So I'm going to move this minus to the outside. So we have now the next term is minus m originally. So we're going to have minus the sum of m with our index m going from 1 to n, and then plus the sum of 6. So now, and the reason for all this is because now we can see that these summations match exactly with what we have, or except for the index variable, they match exactly what we have in the theorem. So what I just circled, that matches with number 3. And it doesn't matter what your index variable is, as long as the index variable is what you have inside the summation. So this first summation, it was simplified to n times n plus 1 over 2n plus 1, or not over, but times 2n plus 1 over 6. The second, so we have my, oh, and it's real easy to forget that I took that minus sign out of the summation, but that's still there. This goes in front. All right, so we have minus the sum of m. So that is number 2. So this is going to be n times n plus 1 over 2. And then if we just add 6, n times, that's just going to be 6n. That would be number 1 in the theorem. And so if you're wondering if you would be given these formulas on an exam, the answer is yes. You don't really need a formula for the first one. That's just so intuitive that just should be obvious. The second one is really good to memorize, but you'll be given all 4 if this problem were on an exam. All right, so that's good if you didn't have to simplify. But now let's simplify, and we have minus 2n squared n plus n plus 2n, it's plus 3n plus 1, and minus n squared plus n. And I'll continue over here on the left. So we have, and I'm going to do several things. I'm going to expand that numerator and also apply the negative. So we'll have minus 2n cubed minus 3n squared minus n. And I'm going to apply the negative for that second term. But at the same time, I'm going to multiply by 3 over 3. Because this is over, this first one was over 6. So we'll have well, actually, I'm not going to apply the minus just yet, but we'll have 3n squared plus 3n over 6, and then 36n over 6. So we have minus 3n squared. Minus 3n squared is minus 6n squared minus n and minus 3n. And then plus 36n. It's going to be 32n. Or let's see, we would have minus n cubed minus 3n squared. Okay. Pretty sure I said 32n. Right here, this was 32n, not 3n. So we have now, dividing that by 2, we have 16n over 3. And that would be the final answer. All right, number 14, compute the following integral using the fundamental theorem of calculus, which is thrown in there so that you know that you don't have to use the limit definition to calculate this. So this is a definite integral. So we're not going to be concerned with the plus c, but we still need an antiderivative. So, and using our properties of integrals, so we can split this up basically into 3 antiderivatives. And you can either just, memorize the formula for the formulas for antiderivatives for these various things that we have. Like in number 15, we'll have an exponential and we'll have a coefficient times 1 over x and so on. But anyway, so for minus x squared, I'm going to start out with the minus. I'll keep the coefficient. I'll put my variable x, add 1 to the exponent, and then divide by that exponent. And you can check this as you go. So if we differentiate this, so 3 times negative 1 would be negative 3, and that's over 3. So that's going to be a negative 1 times x to the 3 minus 1, which would be x squared. So that's altogether minus x squared. So that's what we started with. So that was the correct antiderivative. So for this next one, it was plus 6, the antiderivative of that. I'm going to start out with my coefficient of 6. We have x to the first power. I'm going to add 1 to that exponent to make it x squared, and then divide by that exponent. And that, of course, will simplify to 3x squared. And then the antiderivative for a constant is just the constant times our whatever variable you're integrating with respect to. So this is our antiderivative. And we need to evaluate this according to our limits of integration, and we need to put some kind of notation here to indicate that. There's a few other ways you can notate that, but so what we're going to do now is evaluate this antiderivative at 9, and then subtract from that the evaluation of the antiderivative at negative 3. So I have minus 9 cubed over 3 plus, and this is basically 3x squared. So we have 3 times 9 squared plus 27 times 9. And you're always going to subtract from that your evaluation of your antiderivative at your lower limit of integration. And so you just need to very carefully take care of the sign. So I'm going to put minus. And for me, I just like to say, I'm going to subtract this. I'm going to just put the evaluation of the antiderivative at that lower limit in the parentheses. I'm not going to try to negate each term as we go, because I tend to make mistakes with the signs. So I have minus, here we have a minus 3 cubed, and that's over 3. And then plus 3x squared, our x in this case is minus 3, and plus 27x. So plus 27 times minus 3. And working all this out now. Now it's just an exercise in arithmetic. So this is minus 243 plus 243. It so happens plus another 243. And then here we have 3 cubed, or 3 cubed. 20. Actually, that's going to be negative 27 over 3. And then we negate that and negate it again. So I think altogether we have minus 9. Let me just check that. All right. Okay, so that's minus 9. And then this is going to be positive. It's positive 27 inside the parentheses, and then we're subtracting that. So it's going to be minus 27. And over here we have minus 81, and we're subtracting that. So it's going to be plus 81. And I got 288. Hopefully I didn't make any mistakes. All right, number 15, calculate this integral, which is a definite integral. So there'll be no plus c involved, and we'll need to evaluate our antiderivative at our limits of integration to get our answer. But we'll need an antiderivative, and there's a formula for that. Or you can just say, what, if you differentiate e to the 2x, then you're going to get e to the 2x times 2. And that's not what we have here. So what can we put in this to compensate for that extra times 2? We divide by 2. So we can check this. If you differentiate this, then you're going to get 1/2 times e to the 2x, and then multiply by the derivative of 2x, which is 2. And then these 2's cancel, and you get e to the 2x, which is what we have inside our integral. So that is the correct antiderivative for the first term. And then over here, we have, this is basically 1/3 times 1 over x. Well, we know that, what would we differentiate to get 1 over x? It's going to be the natural log of x. However, this is just a part that you just need to memorize, if nothing else, is that when you are going backwards, going from an integral to an antiderivative, you need to say this is the absolute value of x. So it's the natural log of the absolute value of x. And then what else do you need? So we didn't have just 1 over x. We basically had 1/3 times 1 over x. So I need to keep that in there, so that if we were to differentiate this, we would get 1/3 times the natural log of x, which is 1 over x. And you get your 1/3 x, which is what we had in our integral. So that is the correct antiderivative. And we need to evaluate this at our limits of integration from 1 to 2. So we'll do this at 2. We have e to the 2 times 2. This is over 2, plus natural log of 2 over 3. And then subtract from that e to the 2 times 1 over 2, plus natural log of 1, absolute value of 1 over 3. And And I'm just, okay. And so we have e to the fourth power over 2. I'll just go ahead and put my e's together. So this is minus e squared over 2, and then plus 1/3 times the natural log. And I'll just drop the absolute value, since the absolute value of 2 is just 2, and then minus the natural log of 1 over 3. However, natural log of 1, there is a better answer for this. So the natural log of 1, e to what power equals 1, that's 0. So this is going to be 0 over 3. So I'm not even going to write that last term. And there's the exact answer. If you want to get an approximation, then you can put all this into a calculator and get the decimal approximation. All right, number 16, we have another definite integral. Our antiderivative here is just, it's going to be negative cosine of x. If you differentiate that, then you would get negative sine of x, which would be positive sine of x. So now we're going to evaluate this from pi over 3 up to pi. So it's going to be minus cosine of pi. And then we're going to subtract from that minus cosine of pi over 3. All right, and then cosine of pi is negative 1. So we have minus 1. That's going to be positive 1. And then the cosine of pi over 3 is the cosine of pi over 3 is a half. And then we have minus a half. So it's plus a half. So altogether we have 3/2. All right, 17. We have two functions. F of x is the cosine of x plus 2, and g of x is the sine of x plus 5. Part A, find the area of the region bounded by the graph of f, the x-axis, and the two vertical lines x equals 0 and x equals 2 pi. So let me just kind of make a little sketch to show this situation. All right, so I'm just going to draw the first quadrant here. And we have the cosine function, except it's shifted up by 2. So there's 2, and then there's 3. So at 0, the cosine of 0 would be 1, and then plus 2 is 3. So we're here. And then we have a, let me just kind of also address these vertical lines and these bounds. Basically, we're just going to end up integrating from 0 to 2 pi. Those are where the vertical lines are at 0 and 2 pi. But going back to sketching the cosine, so cosine is 2 pi periodic, so it's going to end up back at 3 in this case. When it gets to 2 pi, and down here at 1, it's going to be at, so cosine of pi is normally negative 1, but then we have plus 2, so that's going to be positive 1. Anyway, the point here is that we just have kind of a shape for cosine. Looks like that. And so part A, and then we have that is our curve for the graph of 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 f, and then we have our x-axis. We have these vertical lines at 0 and 2 pi. So we're looking for this area. So how do we do that? It's simply going to be the definite integral with our limits of integration, 0 to 2 pi, of cosine of x plus 2, and don't forget dx. So our antiderivative here, what do you integrate to get cosine of x? That would be sine of x. And then the antiderivative of 2 is just 2x. And we are going to evaluate this from 0 to 2 pi. So we have sine 2 pi plus 2 times 2 pi. And then minus the sine of 0 plus 2 times 0. And the sine of 2 pi is just 0. And we have plus 4 pi minus the sine of 0. So that's just 0. And then minus 2 times 0, which is just 0. So our answer is 4 pi. And that is the area. Part B, find the area of the region between the two curves and bounded by the vertical lines at x equals 0 and x equals 2 pi. So once again, we have this trig function of sine of x shifted, and it's shifted up by 5. And so at 0, we have the sine of 0 plus 5, so that's going to be 5. And this is just a quick sketch, so I don't really have to be all that accurate. But the point is, and sine also is 2 pi periodic. The point is that we are looking for the area that is between two curves, not going all the way down to the x-axis. So just that blue shaded area. So how can we do that? We can find the area under the curve of G. So this is G of x all the way down to the x-axis. So we would find all of it going all the way down to the x-axis under that blue curve, and then subtract from that what we already found, the area of that pink, the pink area. And we already found that. All right. So as I said, our strategy here is going to be we're going to have the area of g of x, basically, dx from 0 to 2 pi. That's going to be the area going all the way down to the x-axis. And we're going to subtract from that what we found earlier, which was the area under f of x from 0 to 2 pi. So all we really need as far as the integration is to integrate the g of x, which was the sine of x, and plus 5. And don't forget the dx. And so the antiderivative of sine, what would you have to integrate, or differentiate rather, to get sine? That would be negative cosine. And then the antiderivative of 5 is 5x. And I'm just kind of using varieties of notation. So another common way of notating evaluating an antiderivative at limits of integration using these square brackets. C root of 2 pi. So this is going to be minus cosine of 2 pi plus 5 times 2 pi. And then subtract from that minus cosine of 0 plus 5 times 0. All right, so the cosine of 2 pi, and the cosine of 2 pi is going to be 1. And we have minus cosine of 2 pi. So this is going to be minus 1. And then plus 10 pi. And then we'll subtract from that minus cosine of 0. So at cosine of 0, that's 1. So we have a minus 1 plus 5 times 0. So altogether, we have a minus 1 and then minus 1. That's going to be plus 1. So the 1's cancel. So we have 10 pi minus 0. So it's going to be 10 pi. But that is not our answer. So that's just the area under sine of x plus 5. So our final answer is going to be that minus what we found for the area under f of under f of x, the 4 pi. This pink part up here. That's the area that we found earlier that we need to subtract, and that's 4 pi. So that final answer is 6 pi. This is actually the answer to this question up here, 6 pi. Okay, number 18, compute this limit algebraically. And what we're doing here is first seeing if we can plug in 1. X is approaching 1. So can we plug in 1? Well, the answer is no, because then we have a 0 in the denominator. And a 0 in the numerator as well. So we need to come up with something else. Well, you want to take a look and see if you can factor and with the hope of canceling some factors and coming up with an equivalent function that you can plug 1 into. And so that numerator factors very nicely into x minus 1 times x plus 3. And then it's over the x minus 1. So here's our opportunity to cancel and get an equivalent function now. So this is equivalent to the limit as x approaches 1 of just x plus 1. And so one of our rules for limits is even though 1 is not in the domain of our original function, the limits of that original function and an equivalent function, those limits would be equal. So the limit is going to be, we can plug 1 into this. Let me just get it 2. Okay, number 19 for this function shown, find the equation of the tangent line where the point of tangency on the graph of f is minus 3 minus 29. So you can graph this function, but whatever it is, it's going to be, there's a point given, and there'll be a certain tangent line to that point, and we just want to find the equation of that line. That's not necessarily the situation we have. It's just an example sketch. All right, so in order to find an equation of a line, we need a slope and an intercept. If we're going to use the slope-intercept form of a line, If we're going to use the point slope form of a line, then we need the slope and a point. And that's the one that we're going to use here because we have our function. We can get the slope from the derivative. We'll need the derivative, which is minus 6x. And the slope, this is the derivative, it gives us a slope. And at the point -3, our slope, which I'll say is m, this is given by f prime. Plug in that x value where that point of tangency is. And this is going to be -6 times -3. So it's going to be positive 18. That's our slope. And then we have a point that was given. So I'll call this the x1, y1 that we'll need for our equation. Here's our general form for our point slope form. So I'm just going to plug things in now. So the y1 here is -29. So it's going to be minus a minus 29 equal to our slope, which we found to be 18, times x minus a minus 3. So this is y plus 29, 18x plus 3. And it doesn't really say what form to put your equation in. So that would suffice, although we can let's see, 18 times 3. We can put this in a slope-intercept form pretty easily. With plus 54 and then subtract 29 from both sides. And there is our answer. Although this one that answer would suffice as well. Okay, number 20, use logarithmic differentiation to find the derivative of the function that's given there, assuming that assume that x is greater than 0. And this technique is good when you have your variable in the exponent. And we're going to take the log of both sides. So the log of y is equal to the log of x raised to the power of 3x. And the reason that we assume that x is greater than 0 is because we can't have the log of something that is allowed to take on values that are not in the domain of log. So that's why we have to assume that x is greater than 0. So now we're going to take the derivative. And here we have a function y, a function of x. So we're taking the derivative with respect to x. And actually, I could have, there's a couple ways you could do this. You can change this. You can use rules of logs. And the log of something raised to a power, you can take that power and put it out in front of the log. All right. So for the left side, the derivative of log of y with respect to x. So if it was just log of x with respect to x, we would have just had 1 over x. So we're going to start out kind of like that, 1 over y. But because we have the derivative of y with respect to x and not with respect to y, then we apply the chain rule and we put on dy dx. So on the right, we have here a product. So I want to use the product rule. And I'm going to do the derivative of 3x with respect to x. So that's just 3. So we don't have to put on like dx. That would just be 1 anyway. But anyway, the derivative of 3x is 3 times that second function, log of x, plus the 3x times the derivative of the log of x, and that is 1 over x. These x's cancel, by the way, and we just have 3 natural log of x plus 3. And we are looking for the derivative of y. So that's what we're looking for, dy dx. So we need to multiply both sides by y. And there is our answer. Or if you prefer, you can also factor out a 3. All right, 21. The mean value theorem states that if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a number c in the interval from a to b such that what? And if you recall, the mean value theorem is about a function. You don't necessarily have to have f of a equal to f of b. And this is saying that there exists, so if you have the situation and there exists a number c between a and b such that what? And so here's the part that you have to remember, that the mean value theorem, you have the slope of the secant line through those points at a and b. And this is saying that somewhere in between a and b under these circumstances, there is that number c such that f prime of c is equal to the slope of that yellow line that I drew, which is to say the slope of that tangent line, which is given by the derivative of f evaluated at c, and it is equal to the slope of the yellow line, which is going to be the change in y, which is going to be f of b minus f of a, over the change in x, which is going to be b minus a. So once again, so this is saying that the slope of the line at that point of tangent c, which is given by f prime of c, is equal to the slope of that secant line. And so this is going to be the first one. Right, 22, the derivative of f can be interpreted in which of the following ways? So the derivative can be interpreted as the slope of a tangent line. So the first one. And it can be interpreted as the instantaneous rate of change. So the second one. And the long run average of the slope. So that does not describe the derivative, and a point on a secant line through f. So the derivative it does not give us points. So it's just the first two. All right, 23, let f of x equal x cubed minus 4x squared using the second derivative. Determine the open intervals on which the graph of f is concave up or concave down. So if you put this into graphing calculator, just to get an idea of what's going on, you might get something that kind of looks a little bit like this. And so we can see from this graph that it is concave down roughly on this area here. And it is concave up to the right of that point, which we now know is called the inflection point. So there's an inflection point here at some value, and that's That's what we're going to look for. And then we'll say that the interval to the left is concave down, and for the interval to the right, it's concave up in this case. So, and it says using the second derivative. So we're going to need the first derivative, just 3x squared minus 8x. And then from that, we will get the second derivative, just 6x minus 8. And what we know about the points at which the concavity changes, or the inflection point, we know that the second derivative is 0. So we're going to set this equal to 0, solve for x. So x is 8/6 or 4/3. So that's the value now of this point. And we don't just want to make the assumptions based on our visual inspection of our sketch. We want to actually show mathematically then that it is concave down to the left and concave up to the right. So let's pick a test point. So test points. So to the left of 4/3, let's put in 0. And we need to put this into f double prime. And this gives me 6 times 0 minus 8. It's going to be 0 minus 8, which is negative, and that tells us that to the left of 4/3, it is concave down. And then we need to point to the right of 4/3, so f double prime here of 2. It's going to be 6 times 2 minus 8, which is all we're really concerned about is the sign, but this is going to be positive. So it is concave up to the right. So now we can answer our question. It's concave down, negative infinity up to 4/3. It's concave up. From 4/3 to positive infinity. Part B, is there an inflection point? So we found it, yes. There is an inflection point. It is at 4/3. Since that is where the concavity changes. Not only that, and there's actually just a little bit more that we could say here, because and the function is actually defined at that point. There is an actual point there. So yes, there's an inflection point. It's at x equals 4/3. Right, 24, find the following antiderivative. So a good way to do this, by the way, this is an indefinite integral. So when you get to your final answer, don't forget the plus c. But I'm just going to rewrite this first before I evaluate this integral. I'm going to take this 1 over x cubed and just distribute it through. And that will give me x cubed over x cubed minus x squared over x cubed plus 5x over x cubed, and then minus 6 over x cubed. And don't forget the dx. And this is equal to x cubed over x cubed is just 1. X squared over x cubed is 1 over x. 5x over x cubed is 5 over x squared. I'm going to write that as 5x to the minus 2. And then minus 6 over x cubed. I'm going to write that as minus 6 to times x to the minus third. That's all in parentheses. And then dx. And by the way, so there's a reason why I just went ahead and left that term as 1 over x and made the others have their exponents in the numerator. It's because there's going to be a different rule. There'll be one rule for 1 over x or x to the minus 1 either way, and a different rule for the others. So now I'm ready to find my antiderivatives, and with my rules of integrals, the integral of this whole thing is equal to all the individual integrals. So the antiderivative of 1, that's just x. The antiderivative of 1 over x, and this is minus 1 over x. Well, you can just memorize this rule. So just 1 over x is going to be the natural log of the absolute value of x if you're going backwards from, or rather, if you're going from you're finding the antiderivative. You're going backwards from the integral to finding what you would have to differentiate to get what's inside the integral. You can think about what you would have to have. Well, actually, what I was going to say is you just to memorize the formula, then it's going to be the natural log of not just x, but the absolute value of x. And we talked about why that is in class, but you can just memorize the formula. And actually, in a previous problem in this review, we had 1 over 3x, and we talked about how that is handled slightly differently. But anyway, so the antiderivative there is natural log of the absolute value of x. For this next one, the antiderivative plus, I have a coefficient of 5 there. I'll go ahead and keep that. I'll put down my variable, the minus 2 exponent. We're going to add 1 to that when we're finding antiderivatives. So this goes to minus 1. And then put this over that exponent of minus 1. We can check this, by the way. What is the derivative there? It's going to be minus 1 times 5, which gives us a minus 5, but that's over the minus 1. So that would give us positive 5. And then we subtract 1 from the exponent. So we have 5x to the minus 2. And that is what we had there in our integral. So that is the correct antiderivative. Same idea for that last term. I have minus 6. I'll put down my variable, add 1 to that exponent, which becomes minus 2, and then divided by minus 2. And then plus c. Don't forget the plus c. So I'm just going to simplify this a little bit. And there's our final answer. Right, 25. Since the tangent of x is equal to the sine of x over cosine of x, then it is true that the derivative of tan x is equal to the derivative of sine of x over cosine of x. And you could just memorize what the derivative of the tangent of x is, but this question says derive it and use the quotient rule. So we are looking for derivative of tan x is equal to the derivative sine of x over cosine of x. And then the instructions say to use the quotient rule. So we have the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, which is going to be minus sine of x, and then all over the denominator squared. So this is cosine squared. And so we have the cosine squared of x, and then minus sine times minus sine. So it's going to be plus sine squared of x over cosine squared of x. So you can actually do this a couple of ways. One way is to recognize that cosine squared plus sine squared, that's a trig identity equal to 1. And then over cosine squared. And 1 over cosine is secant. So 1 over cosine squared is going to be secant squared. Another answer, by the way, is to take cosine squared plus sine squared over cosine squared and split that up. You have cosine squared over cosine squared, and then sine squared over cosine squared. And this is 1. And sine over cosine is tangent, and this is squared. So this is tangent squared of x. That is another valid answer. And so that's it. But just by the way, just FYI, so we have just seen the derivation of some trig identities. Or the secant squared is going to be equal to 1 plus tangent squared.